Welcome to a new episode of the third season of Zeroing In, the science podcast. Today, we are in conversation with an expert and a brilliant researcher from the fields that take roots in mechanical engineering and aerospace engineering, the realm of kinematics and optimization, Professor Kurien Issac. Professor Issac completed his bachelor's from the College of Engineering in Trivandrum and went on to pursue his master's in mechanics and design from the Indian Institute of Science in Bangalore. Following this, he spent some time at the Tata Consulting Engineers before going further for his PhD to the Indian Institute of Technology in Madras. He studied the optimal synthesis of linkage mechanisms for his PhD, and after this, took up a faculty position at the Indian Institute of Technology in Bombay. Professor Issac currently carries out his research at the Indian Institute of Space Science and Technology in Trivandrum, where he holds the position of a senior professor. Throughout his research work so far, Professor Issac has worked on, studied, and even created quite a number of novel mechanisms ranging from variations of four-legged robots to those of ornithopters. His research directions span the wide arenas of optimization techniques and designs, robotics, mechanism control, humanoids, and landing rovers as well. In our conversation with Professor Issac, we go on a breezy ride through some very internal understandings of the mechanical world, introducing us to the gears of our fast-moving lives that are enabled in many dimensions by the excellence mastered by the researchers and engineers practicing in the field. It was an absolute pleasure to uncover some exceedingly intricate ideas which Professor Issac articulates with stellar insights and inspiring humility, lined with equal amounts of fascination. Your hosts for this episode are Shreya Mishra, a scientist at the Physical Research Laboratory, and Manish Kumar Mishra, who is currently pursuing his master's in Computational Science and Engineering from the Technical University of Munich. This is Zeroing In, the science podcast.
Sir, before we move into the technical bits of the conversation, I would really like to ask here, maybe I think this is kind of a trivial question, but it's related to one of the mechanisms that we often see around. So the question being, why is it so difficult to understand the flight of a bird?
Yeah, so my understanding is the following. The aerodynamics associated with bird flight is very complex. It is not steady like most aircraft cruise flights are. So you have unsteady aerodynamics. And the way the bird, a medium-sized bird, moves its wings is very complex again. There are joints in the wings, so they flap, they do what is called feathering, and they flex the elbow, extend the elbow. There are so many things which happen as a bird flies. So all this put together makes understanding the aerodynamic forces coming on the bird very very difficult, both to experiment because usually it is low, what is called low Reynolds number domain, where experiments and analysis are more difficult. So all this makes it more difficult to understand. But people have done amazing work trying to understand this, putting birds in wind tunnels, putting certain sensors on the body to understand how the flexing happens. So some amazing work has been done by people in aerodynamics as well as people in biology.
Yes, sir. Sir, can you also at this point talk about your research objectives when we come to ornithopters?
Yeah. So people have been able to make relatively smaller systems, bird-like flapping wing systems, fly reasonably well. But when it comes to larger systems, it becomes more and more difficult because the mass goes up as cube of the size, whereas the surface area is what determines the forces which help the bird keep aloft, and that is proportional to the surface area, which is square of the size. So this you typically have. In fact, that is one of the biggest issues in man trying to fly itself. If you look at the earliest attempts of man trying to fly, it was trying to put big wings on people, on the arms, and try to flap it and see whether people can fly. And one of the greatest persons who has done it is Leonardo da Vinci. But technically, with the kind of muscle power we have, it's next to impossible to do that. So making the larger ones fly is still a big challenge. Although one of the earliest work in University of Toronto by a professor called D. Laurier concentrated on that, and he even built a big sized one-man seater aircraft kind of a thing, which sort of hopped off the ground but couldn't fly. But I feel that direction probably is not all that fruitful. When this is my sort of feeling. That is making bigger things fly with flapping wings.
Yeah, mostly what we do is we adapt mechanisms from the nature. Basically, we copy things. So this came out of curiosity because our flying objects, which are basically aeroplanes, do not exactly imitate the mechanism of the birds that we naturally see in the outside world. So this is something contradictory. That's why we had this, like, where are we humans engineers lacking behind that we could not imitate that?
Yeah,
And
Shreya,
that is where
actually,
perhaps.
even our the way the airplanes fly is also somewhat modeled on how birds fly. If you look at how a
Okay.
kite glides, okay, that is
Yeah.
almost exactly how an aeroplane also would glide. So the idea of getting lift by forward velocity, holding the wings at a particular angle and getting sufficient lift is something birds themselves use. If you look at an albatross, it finds it very difficult to flap because the wings are very large and it hits the ground if it tries to flap too much. So you should see the way an albatross takes off. It's almost like an aircraft.
Before going forward, I have a question along the same lines, on the same topic. So, apart from improving our understanding of bird flight, what do you think is the motivation for pursuing research in ornithopters?
Yeah, so the medium and smaller type ornithopters we will be able to make and fly, and they have very important surveillance applications. So if you look at a quadcopter or a fixed wing aircraft flying around, a drone, then people immediately are suspicious. But if they see a flapping wing, a small bird fly, they may not be able to distinguish and see that it is an artificial thing. And so surveillance is one of the critical things. So that is what I understand. I'm sure. So see, whenever somebody says something cannot happen or something is restricted to a particular application, somebody will come along to prove him wrong. So I just this is the current perception I have. I hope somebody comes and proves me wrong.
Okay, sir. At this moment, we would like to go back a bit and talk about your PhD thesis, which was titled Optimal Synthesis of Linkage Mechanisms. So, could you briefly explain what it was about and what was your motivation to take it up?
So kinematics is something I fell in love with because of a professor. So my master's project guide, he also took a course for us in IIST Bangalore, was an excellent teacher. There's often teachers who motivate, and I got very fascinated with kinematics, and I did a project in kinematics with him. So when it was time for me to do PhD, I wanted to work on a class of mechanisms he was not working with. So he suggested that I join a faculty in IIT Madras who was actually a very good researcher in that area. And I joined him, and I wanted to work in kinematics because I was very fascinated with that. And then he gave me a problem which was very practical and very result oriented, whereas my mind was always thinking more about how to develop methods and approaches and procedures. So I started working in that problem. And so finally, the kind of problem I ended up solving in a very broad sense is called mechanism synthesis or dimensional synthesis of mechanisms, which is essentially the following. If you want a mechanism to perform a certain kinematic function, relative motion, then given the mechanism, what should be the optimal dimensions of the mechanism, which will make it do that function? So, in a sense, it is curve fitting. Like if you have a set of data points, you try to fit a straight line through that. Here we try to fit fairly complex functions through a desired function. So it is again in mathematics a larger area called approximation theory. That is what the problem falls in mathematically. But any engineering problem have has ramifications which go beyond just mathematics and physics. But I was confined to just kinematics in this particular problem. And the critical thing about the problem was that I found if you formulate the problem in a particular way, which appeared to me to be the most natural, then the problem becomes very difficult to solve. And I found that very few people really solved it with that kind of a definition of the problem. So I was able to go deeper into it and come out with an algorithm which was able to solve it very effectively. So that was essentially what I did in PhD. If you don't want me to go into more details.
That's okay, sir. But so we do understand that optimal synthesis. So in some sense, designing the an optimal mechanism was an important part of your PhD. Today, when we think about optimization, we are always like thinking about computers, and but you completed your PhD in 1988, and it's very interesting to us. What kind of computational tools did you use, or how if there were any challenges that you encountered during the work?
Yeah, actually, even at the end of BTech, I had started working on computers. There were small mainframe computers. Then in IIST in Masters, I worked on a fairly large computer. I think it was IBM 370 or something like that in IISC. And again, I was working on mainframes with cards. You write the program on cards, one line per card, that kind of a thing. And cards are read and programs are executed. So we used to get very little time or slots in the computer because a lot of people in the campus would want computer. We used to go at 4 o'clock in the morning, stand in queue, get a slot for half an hour, then have breakfast, come back and work. But luckily, I started PhD in '84. By '85 or '86, I think, a desktop computer came to my lab. I was very, very lucky. So from then on, it was very fast. So.
Okay. Sir, would you also explain us a bit about the kind of optimization we are talking about here?
So this may be useful to you also. If you look at typical way people solve complex optimization problems in design and mechanical aerospace design, you'll see a lot of what are called meta heuristics techniques being applied. These are genetic algorithms, simulated annealing, particle swarm optimization, things like that. And what I find is that most of the people do it without sufficient understanding of the problem they are trying to solve. If they spend a little more time on trying to understand the nature of the problem, they may not use these techniques at all because these techniques are basically random search techniques. You pick up search directions using some amount of randomization and some amount of information which gets gathered as you progress. And you don't really make use of information which could be very, very useful for doing optimization. So this sort of more or less happened when I did PhD also. I told you that I picked up a definition of the problem which was actually quite difficult to solve. So it turned out that if I define it that way using a particular norm for functions, then it turns out that the objective function which I formulate is non-smooth. It is continuous, but gradient is not defined everywhere. So it is non-differentiable. And typically, one would try to use a meta heuristic technique to solve that particular problem. At that time, I was not aware of those, and they hadn't come up. There were other techniques also available. But when I try to understand more and more about this particular type of function, I luckily again chanced upon a paper which actually addresses how to tackle these kind of functions using gradient based approaches. So if you actually pick up the gradient when you try to solve optimization, you get a lot more information than these meta heuristic algorithms are able to gather. So then that actually opened a huge path for me. Plus, I was again lucky that when I was in IIST, when I was attending the course on optimization, which was another very good course which I attended there. I mean, in the class, I had a very random thought on an approach which I can try out for doing optimization. It turned out that precisely that approach was what was very useful for this particular problem once I understood that is the way it was. And so I was able to then develop an algorithm which actually solved the problem extremely well. Technique I developed is for non-differentiable objective functions and constraints. I then wrote an algorithm which is a little complex. If I solve it nowadays, I will do it different. But the basic ideas are the same.
So, sir, before we move forward, perhaps in an indicative manner, can you briefly point out your career trajectory? Like how was your childhood, like starting from there? So, just to consolidate it all.
My career trajectory has been always as a teacher and a researcher. So nothing much in terms of the type of jobs I have been in, except for a very short period of 7 months. I worked for a company called Tata Consulting Engineers. They were project engineers. I wanted to pick up some design experience and then go for PhD. But the kind of experience I was picking up was not the kind I wanted. So I worked only for 7 months. So otherwise, it was in academics. So within academics, my career progressed significantly because I joined academics to work only on kinematics. I was very narrow-minded and very focused and wanted to work only on kinematics at that time. But I was very lucky. I got into a team of three other faculty, and two of them were very, very practical engineers. Two of us were very impractical engineers in the sense we never were exposed to much practical engineering. We were more of, I mean, modeling, analysis, and numerical methods and things like that. Whereas the other two faculty were very experienced and very creative and very much oriented towards design, getting new ideas, solving problems, building artifacts, products, testing them. So they were real engineers. So I was very lucky I got into this team because almost, I mean, half of the learning I have had as a teacher was working in this group.
So, sir, this was when you were at IIT Bombay.
When I was in IIT Bombay, yeah. So we had a team called the robotics. There was a robotics lab which we set up, and our team was the one which actually set it up and ran it. And we had so many good students and project stuff. Yeah. So in a sense, I learned a lot from that. So I migrated from kinematics to many other areas. So dynamics is one of them, which I was anyway very fascinated with at the beginning. Then, because I was teaching robotics, I didn't have a background in control, but control is essential for robotics. So I learned and taught a course in BTech in control, and got to learn that and got to use it with many of my project students. And of course, I went further in dynamics and control and optimization and kinematics. These are actually the areas in terms of subdisciplines in which I worked.
I would like to point out that, as you said, that you were very narrow when you started out and you were very strict about kinematics. Looking at your research, no one can say that it was narrow minded, given how many detours you've taken at every point, to be honest. But, sir, I would like to ask, how did you even get involved in this whole kinematics? Or how did you know, like, starting from your schooling years, how did you know that, okay, kinematics was something to take up?
So, like most of us, I joined engineering because I was good in mathematics and physics, not really because I was good in engineering. Although I sort of dabbled with a few things and spoiled them in my home and got roundly scolded, and so that sort of shut me off in that direction. So I really hope a lot more people who are tuned to engineering and artifacts, how things work, how they are made, they come into engineering programs. But like most of us, I was fascinated with physics and mathematics, and in physics, what I really liked was mechanics. I found it very comfortable, and so that is what took me to mechanical engineering. And again, in mechanical engineering, what fascinated me were topics where very good teachers were there, and this turned out to be in thermal and fluids. So thermal and fluid is one area in mechanical engineering, and there were very good faculty for that. and I was really fascinated with that. And you become good in things you are fascinated with naturally. So towards the end of engineering, I was BTech. I was more fascinated with thermal fluid, but I ended up doing a project which required some modeling and simulation. So I came back to mechanics, and mechanics anyway was what I really liked in physics. So I then, when I went for masters, I joined machine design as the program. Yeah, I mean the program machine design, and within that, as I told you, I had an excellent teacher who became my project guide too, and he of course inspired a lot of us. And his name is Professor T.S. Mrutyunjaya, who was a professor in IIST, and because of him I really took up kinematics. So this is how I got to kinematics, and like anybody should, you should explore many things before you home in on one thing.
Yeah, yeah, makes sense. But sir, looking at like how you've moved from your BTech to your masters to your PhD, it's a very smooth transition when you look at least from a distance. That there is not a gap in between the years. It seems like a very properly packed and a planned thing. So was it that way, or how was it like?
So I was definitely interested in research when I did that BTech project. One tries to understand something by oneself, try to get some independent thought, try to come out with methods of attacking something, come across problems which you have to solve. So the process of doing a project, trying to understand a problem and tackling that, I was really fascinated with that. And so I really wanted to do research, but I was not sure where to do research. So eventually I knew I would like to end up doing research. I was not very sure, but when I was in IISc, I saw an environment which was really good, where faculty were doing teaching and research. So I thought I also should get into a good educational institution and do research. I was not very keen on teaching actually. So although I went for a short while, I worked in a company. The kind of practical experience I wanted, I was not really getting. So I immediately joined for PhD. So the only gap you will find in my career would be that 7 months where I thought I didn't learn much, but I mean, 6 months after I quit TCE, I realized how much I had learned there. So many times you don't realize how much you learn till you sit back and try to look back on that. I mean, like you implied, my career was almost one track.
So, we have seen that you were involved with several research areas during your time at IIT Bombay, from design and analysis of mechanisms, walking robots, ornithopters, and to something like piezoelectric actuation of curved beams and several other topics. But before delving deeper into the problems itself, we would like to know what is it that you look for in a project before starting.
Actually, I don't really plan a project in that way. If something excites me, meaning if something appears very challenging and is my larger domain of interest, then I tend to take that up. So it is not that. That is initiating a project. But once, of course, you initiate a project, you plan things. What has actually occupied my mind a lot in IIT Bombay as well as IIST, not in IIT Bombay, are robots which use legs. So that has been the maximum amount of work I have done with students has been in that area. So the larger domain in which I am, if I find something fascinating, I explore that. If it appears to be something worthwhile, then I may take it up. So, but even though I say that, those kind of things happen through student projects. I worked on two major projects in IIT Bombay. One was again developing a six-leg walking machine. So as I said, I was already fascinated by that because there's a lot of kinematics in that. There's a lot of statics in that, very slow moving vehicles. A bit of dynamics, but not much. Quite a bit of geometry, and it is very fascinating to me. And so I had students who took up problems in that, and I was lucky. The other three faculty I was working with, two of them were again also fascinated with that. So all four of us wanted to work in that, and again our team was lucky that Almost next door to IIT Bombay is BARC, which had this unit DRHR, Division for Remote Handling and Robotics, headed by somebody who was as fascinated by walking machines as we were. He was a very senior person there, and we collaborated, and they funded us on this project. Although it took a long time, because at that time the kind of subsystems available for us is actually nowhere near what we get today, which we can buy by a click on the computer. We had to, for example, as the major motor, major two motors that we used for the robot, we had to actually use a drilling machine motor and then convert it to a servo motor and develop it ourselves, more or less altogether. It was so much more difficult to do it at that time, but we went very slow but steady, and finally we were able to make that machine, which made big waves in India and abroad. And it was a huge learning curve. So we knew that it was a big project. A lot of people had to contribute. So something like 4 or 5 faculty were there, and the total team, including students, everybody, was of the order of around 45, 50 people. Not at one time, but over the years. The other major project which I did on switchgear dynamic analysis, both experimental and theoretical or numerical, actually came to us as a consultancy project initially, where we developed a small program for dynamic analysis of a small switchgear in BHEL, Hyderabad. And because that was a success, um, I mean, there were discussions happening on further work by other switchgear companies, and this actually finally snowballed into a major project. And this was another major project I worked in IIT Bombay. So these are major funded projects.
That's actually very fascinating, sir. And when we were actually going through your research, one thing that caught our attention was the hopping robot. So some of us were really interested to ask, like, how does it work? How does it remain stable?
So it's quite amazing that so something about the leg robot is that the six-leg robot moves very slowly, ensuring that it is keeping balance at all time. So which requires at least three legs to be on the ground, and the center of gravity of the body and the legs together to be within what is called the support pattern of the legs. So you move very deliberately, slowly, and no dynamics comes in, and you're able to keep balance, which is the biggest issue in walking machines. And once you're able to keep balance very easily, the rest of it becomes very easy. And this is why bipeds are difficult to develop. So man himself actually getting free of two of the appendages, the arms, and lifting them up and walking on 2 feet was a major step in evolution, and that was what made our brains much bigger. Okay, so walking with two legs with small feet requires balance. It requires sensors like the ear that we have, the eyes, and very very good perception and ability to coordinate our motion to keep balance. So developing biped robots are very difficult. So imagine one leg robot cannot keep balance at all if it is stationary. Okay. So it was developed first by a person called Mark Raybert, one of the top robotics researchers in the world. So Raybert in Carnegie Mellon, as a student, developed this hopping machine, one-leg hopping machine, which has to keep hopping in order to be balanced. If it is not hopping, it cannot be balanced. Okay, so he developed that. Then he left Carnegie Mellon, came to MIT, and then he was the person who started Boston Dynamics, which makes amazing robots.
Right. Sir, coming to Boston Dynamics, we see there's a lot of research on biped robots, which kind of matches the popular science and media perception of what a robot is. Did you ever consider or were involved with biped robots, and what is the difference that you see between like a biped robot or a multi-leg robots?
Robot of the type which Boston Dynamics and some of the others have done, which are dynamically stable. Okay, and the Boston Dynamics robot can do somersaults. You must have seen it on YouTube. So it's an amazing development. Even single leg hopping robot which Raybert did was an amazing development, and he and his team only developed that Bipod robot. But before Raybert, others had developed Bipod robot. But Asimov, you must have heard of the robot Asimov by Honda. But Asimov was not really all that dynamic. It was moving very slowly and deliberately with fairly large feet. But of course, they later made it run with a lot of difficulty. So I haven't very seriously thought about making bipeds, but I was very interested in making four-legged running robots like horses and dogs. Okay, but I didn't proceed very far in that because even trying to simulate and trying to understand was not very easy. So I have had students sporadically on this, but I haven't progressed very much on that. But that is one of the dreams I had, to make a four-legged running robot. But if you look at Rayber's robots, there is the big dog, which I don't know what it is called later on. When the big dog was just being put through its paces, I had been to Boston Dynamics, and I had met Raybert and others and see Big Dog being put through its paces. So that is the kind of robot I wanted to make. But I mean, at that time, Raybert was using hydraulics in order to power his joints, and typical robots that he developed were big, uh, very big robots. Later on, he started using electrical motors, and he is now making much smaller robots and very capable. So this is a very fascinating area. It is very challenging even now. Imagine a mountain goat. You must have seen a mountain goat moving on mountains. It's amazing, the kind of balance and ability to find footholds, and very tiny footholds. How it is able to keep the hoof there is an amazing thing. So nobody has made a mountain goat type of a robot. It will take time. But these are the kind of challenges which I am sure some good engineers will come up and solve.
So you mentioned that you were quite fascinated by four-legged running robots. So like different creatures, if we see four-legged creatures, run in a different style. So can you briefly talk about if you've researched in this type, what are the styles?
A single four-legged creature, the horse, runs with many gaits. Okay, so it walks, it trots, it canters, it gallops, and there are many. I mean, each of these has different variations also. So if you have four legs, if you have three legs, I mean, it becomes a little more dynamic. I mean, there are no three-legged creatures I know of, except kangaroos do use the tail as a third balancing thing. So four-legged robots can walk with static gaits, which doesn't require dynamic balancing. But when it picks up speed, it has to pick the feet off the ground more often. And there would be times when just two legs are on the ground, or even one leg is on the ground, or in gallop, sometimes no leg on the ground. So not only that, you must have seen cheetah running. So cheetah, the way it bounds, okay, it throws forward the front leg at one time and then grips the ground, and then the back legs come forward. And when you see the back leg coming forward, look at the back of the cheetah. It is so bent, almost like a semicircle, and then it powers itself off on the back leg. It's an amazing thing to see it run in slow motion and still keep balance and still turn as the antelope suddenly turns. Truly amazing. So these are things eventually I am sure we will also be able to do. But right now we are on the path in that direction. And there are certain dangerous directions, like using these things for war and things like that. And yeah, it is an area of research people have to be a little careful about.
It's quite fascinating to see how you are equally fascinated by all of these natural beings around and how much you've observed them through the time.
Somebody working on robotics has to, because that is the fountainhead from which all the a lot of information comes to us.
True, true.
So before we move on to next question, I would just like to ask, like among all the robots that you have come across, is there one that stands out, one that you found really elegant when you came across it?
So the earlier robots were just like our arm, okay, and then there was a company called Adapt, which tried to make it very fast and with high acceleration. and they achieve it with a slightly different configuration called what is called the cylindrical configuration of SCARA, and with a few interesting innovations of how they drive the joints with the motors, and that was a very fast and very elegant robot. And then there are people went beyond just serial robots and started developing what are called parallel configuration robots mechanisms. And there are a couple of extremely elegant and very fast robots, both by Adapt and other companies, which are what are called parallel robots. Okay. The other fascinating robots which I find are the walking and I mean, not only walking robots, but the robots of the type which Boston Dynamics developed. Even the rover which went to Mars, the configuration they have sent to Mars hasn't changed at all. Okay, the only other configuration, two configurations which was sent to terrestrial region beyond Earth, was to Moon. The Russians sent a rover called the Lunar Code, which had 8 wheels, and the Americans sent a self-driven, astronaut-driven four-wheeled vehicle. But if you look at the configuration of the lunar rover, I mean the Mars rovers, that is again very, very elegant. It ensures that all the 6 wheels are on the ground at all times, and all of them take reasonable normal forces so that they can develop reasonable traction in order to move forward. So that is another extremely elegant design.
Yes. I think this is a good point to move a bit ahead and ask you about your current research. So, would you like to talk about what are you working on right now?
Yeah, I'll be retiring in 1.5 years, but I hope to continue working. So, I really want to, at least theoretically, because once I retire, I will not be able to do this by making things, but at least theoretically get back to the problem of four-legged running and make at least on in the computer simulated robots which can run with great dexterity. That is one of the problems which I am still fascinated by. But a larger domain which I picked up about 20 years back. Initially, although I was working in kinematics, and some of the problems I worked in robotics required velocity analysis or statics at the most. I actually, at that stage, thought I should work on dynamic systems where the optimal design problem has objective functions and constraints which comes from some aspect of dynamics. So there's a whole region, whole area of optimal control where dynamic systems are controlled, and what they try to do is try to find out inputs which control a dynamic system. Whereas my focus was on design, so it was input will be there definitely, but in addition to that, I wanted to ask the question: how do I design this robot so that it is taking minimum energy or minimum torque and things like that, and in a dynamic situation. So I worked on a large number of things which were dynamic systems and design of those dynamic systems. So that is a larger area in which I worked. So I want to sort of consolidate that kind of understanding I have gained in that area. I work with students on different problems, but I haven't sat down and consolidated all that. So this is another thing which I am very interested in doing, because I've also looked at a few aerospace kind of problems, and I have worked out with students some ideas which I've had, and some of them seem to be very interesting. So I want to put some of those also a little
That's
forward.
actually very interesting, sir, because in general, what I've seen is people usually design as not really accounting for the dynamics, and they sort of try to get around it at a later moment. So it's actually interesting thinking about if you can take that dynamics that you want to control at a later time in the design process itself. Sir, you have also been involved with rovers, design of rovers in your recent years. We came across it in your paper. So, would you like to talk about what the work research was on?
Yeah. Okay. So the rovers which I have been looking at for quite some time are wheel rovers, because these are very relatively easier to control and move. On the other hand, If you have a leg robot in place of a wheel robot, then you have a lot more actuators, could be more heavy, and it's a little more difficult to control, but it may be more capable. It may be able to climb a cliff, which a wheel robot is not able to climb. The kind of work I did in wheeled robot. So let me kind of sort of give you some insights on the problem my PhD student and also my colleague Sam Noble sir worked on. So there is the problem of controlling a wheel robot. So a wheel robot is already there, let's assume, and it is on an uneven terrain, maybe a hard terrain or maybe a soft terrain with sand. The problem with sandy terrain is that if the wheels spin without going forward, then it digs a pit and then gets sunk into that, and it may not be able to get out of that rut. So that is a very serious problem with Mars rovers, and two of the first Mars rovers died. The first one died because of this. But let me come back to hard surface and let me say what the problem is. So already we have motors on the robot, on the wheels. There are certain sizes for the wheels. We are on a particular terrain, so there is some amount of grip that we have on that particular terrain. Okay. Now we ask the question: can I move further forward by applying torques, various torques on the motors, without the wheels slipping? Okay, this is a very serious thing. Not even on a sandy terrain. Sandy terrain is a serious problem, but even on a hard terrain, you wouldn't like a wheel to slip because that may make the whole rover turn in a direction you don't want it to turn. You want to make it move deliberately the way you plan. So this is a problem. What are the torques to be applied to ensure that all the wheels move properly without slipping? Okay, so this problem was formulated by many people, and Dr. Sam also, in a way which again we most of them formulated that way, but they we found did not solve it with sufficient understanding of the nature of the problem. So he was able to come to solutions which other people hadn't got. So this is one problem. The other problem that he tackled, which is a level more complex than this problem, is that suppose you have that think of a rover, but you haven't yet designed it. Okay, so in addition to just operating the rover without slipping on a hard terrain, uneven terrain, you also want to ask the question: what are the optimal dimensions of the rover? Okay, that is a design question, whereas the first is an operation or a control question. So to do the design with the control subsumed in that is a more complex problem. And again, some people have solved it. Sam Nobles has solved it in a very detailed way, in a very rigorous way. So again, I mean, these are problems which are very narrow and very small in the larger domain of rovers. So if you look at rovers per se and what people have done on it, I've already talked to you about three types of rovers people have already put on Moon and Mars. There are many rovers which have been proposed. Okay, one very good group in is in Switzerland, and they have proposed many fascinating types of wheeled machines which can have balance and which is able to negotiate very uneven terrain. And at the beginning, even before the European Space Agency, along with the Russian entity, together actually proposed a large number of very interesting mechanisms for rovers. Okay, all of them have not been tried out yet, but slowly, because sending something to space is a major effort. And so, unless you are extremely sure you don't do that, the Chandrayaan rover that we were trying to send in Chandrayaan 2 was the type of rover that was sent to Mars. That is called the rocker bogie suspension. And of course, unfortunately, we didn't have the experience of that landing and moving around on Moon because the Chinese rover has moved around on Moon. That also has a somewhat similar configuration. So there are very fascinating problems on not just rovers. There is an effort trying to see whether you can develop systems which can dig into the subsurface soil of Mars or Moon and collect samples and analyze that. For example, collect ice and core it and then analyze it. So there are things which are based on, again, a biological system called the slug, how its motion is used to make a robot which can dig into the ground. A couple of my students have actually worked on that. So there are very, very fascinating problems related to deploying robots on Mars or Moon or other planets.
So, sir, as you pointed out about Rockabogie rovers being used in a lot of Martian missions. So, one thing which I've been curious about is that usually we hear that these are very slow. Is the reason for that just that they want to maintain a certain level of downforce and stay on track? Is it just the uneven terrain, or is there something else to it?
Yeah, one is uneven terrain, the other is sand. So, and you have sent something so far away, you don't want to risk almost anything. So, the way the Martian rovers are moved is very, very deliberate and very slow, something of the order of 2 centimeters per second or even less, I think. Whereas lunar code on Moon was almost directly controlled real time from ground by Russians, and that could move much faster. And the lunar roving vehicle, which was taken by Apollo program to Moon, was driven by astronauts at very good speeds. But if something happened, astronauts were there to do something at least. So much of it depends on how much it costs to take risks. Unless we set up a domain there, a habitat there, and there are people there who can repair it, and then we will make it move fast.
Sir, we would like to talk about your experiences now, while moving into a bit of a personal side. So I'd like to ask here, when you remember of your early years, what are the things that you often recollect?
I am slightly disorganized as a person, so I would only take up things which interests me. So I would be pretty late submitting assignments and things like that, but I would do those things myself. So, but I was fascinated with studies generally. I was fascinated with new concepts. So every semester before the semester was the most exciting time for me, because I would go to library and pick up excellent books, and I would bring them home and I would try to read them. And I used to really find new things very fascinating.
One thing I would really like to ask is, you said that you had your mindset at a very early age in career that you want to work in research and you want to be a full-time researcher. But you also mentioned that you never thought of teaching. So how did you come about and when did you come about to this whole idea of teaching?
Yeah, so it was actually taking a risk. So I had difficulty facing people, facing large number of people, not one or two, but facing a crowd and speaking to that. I had stage fright and things like that. So I wasn't very sure I'll do well in teaching, but because I wanted to do research and take up problems which I am fascinated by and not handed down to me, so independent. The only place I could do that was in academic institutes, and so I took the risk. But when you're full of what you want to teach, you don't have stage fright. So I mean that naturally goes away. So I didn't have problems really, and then I found teaching very fascinating too. So and one tends to look at things in more detail and more clarity, because you want to convey concepts. When you try to teach, you actually internalize things, concepts with greater clarity. So let me tell you about two excellent professors I met in IIST Bangalore. So one of them was very, very systematic, worked in the area of stress analysis. His board work was so perfect. He would spend the first 5 minutes on what we discussed last class, and then tell us what we are going to discuss today. Then he will discuss that. At the end of that, 5 minutes before the class, he will stop and say, "This is what we had discussed today, and this is what we are going to do tomorrow." So perfect. Okay, it's almost like if you had photographed his board work, you could have converted it to a book. It's almost as good as that. So he was a very famous professor in IISc. And then another professor, again very well known, was in turbo machines. He would come to the class with a chalk, nothing else, And then he would actually wave his hands and build up the whole subject in front of you in such a beautiful fashion, okay, and inspire you. And he was totally not interested in organizing his class. He will just pick up things and talk to you about it, tell you about motivations why people address things some in a particular way, and how one might approach how to answer that and things like that. So these two people were diametrically opposite, and both very effective teachers, both very inspiring. So what I spend most emphasis on is actually what is the question that we are trying to answer, and then try to motivate the question, because I feel often that if a question is posed with sufficient clarity, okay, and sufficient understanding, solution almost always occurs to many people. It's not necessary that you have to push a particular method of solution. Students themselves will be able to think about, yeah, if I approach it this way, I'm likely to move in this direction. So to my mind, trying to understand the problem is more than half of trying to solve something.
This was a conversation from the third season of Zeroing In, the Science Podcast, where we discussed some of the fascinating questions and insights with Professor Kurien Issac. We extend our sincerest gratitude to Professor Issac for sharing his ideas and understanding on the intricately hidden world of mechanisms. On behalf of the Zeroing In team for this episode, which included Manish Kumar Mishra, Pranav Kopa, Sankalp Hongal, along with the core team of Zeroing In, and I am Shreya Mishra. Thanks a lot for listening to this episode. We'll be back with a new episode next week with further interesting questions and conversation with eminent Indian scientists from across the world. If you have any suggestions, you can visit us on zeroingin.org or write to us on zeroinginpodcast@gmail.com and follow us on our Instagram or Facebook handles @zeroinginpodcast for the latest updates.